Hi everyone. All right, this lecture is for the 19th of February 2020. This is Wednesday's class, number 16. Because of Engineering Career Day, we're not able to meet in person today, so we'll do this one online. Just looking at these announcements, remember that your assignment number 5, Evaporation and Infiltration, that's due today, assuming you're watching this on the 19th. Our midterm exam will still be, as originally conceived, on Friday. We're going to have it in class on Friday. It's covering classes 1 through 16, which is including today's material as well. As I previously announced, about roughly 35% of the points are going to come from conceptual questions. The balance will be from problem-solving questions, and you need to be able to have all the software that we've used so far this semester. So please come to class prepared to solve an HY8 problem, a StormCAD problem, using Excel, all the software tools, all the material. It's fair game for our exam on Friday. If you have any questions about that or anything at all, please let me know. I'll have office hours. I'll be responsive to emails, so just let me know. Now, today's class is an extension of the infiltration topic. You may remember that on Monday's class, what we did was we jumped ahead to the problem solving involving the green-amped method and the Horton method, just so you'd see a couple of example problems to help you through that homework. So now in today's class, we're going to kind of rewind a little bit and get into some greater detail on the fundamental principles of infiltration and what are the forces that drive infiltration, kind of a little bit more on the theory there. So this important information will be included on the exam, so I encourage you to take careful notes, and as always, let me know if you have any questions.
How much water is coming from the sky, and where does it go when it hits the surface? And actually, even before it gets to the surface, there are some other abstractions it can encounter. You know, like the water can have to wet the outside of a tree. That interception is an important abstraction. There can be water having to wet the surface of a building. When there is a lot of skyscrapers in an urban area, then that can play an important part of reducing the amount of precipitation that gets to the ground level. But eventually, some water is going to get to the ground. And so we need to know how much of it's going to infiltrate into the soil, because whatever doesn't infiltrate is the problematic runoff that can cause flooding on the one hand, or can be an important resource for irrigation and for storing and capturing water to be used later. We'll just revisit a couple of concepts that I'm sure you've seen before, maybe in a soil mechanics or a geotechnical engineering course. What we will look at is how the soil properties influence the movement and behavior of water. And you probably remember that what's unusual about clay particles is how small they are. And clay particles, because they're so small, they have a really strong charge. Whenever you have like a colloidal particle, like a clay with a really small particle size, it has a strong negative charge on the outside. And so these electrostatic forces affect how water is able to move through the clay, because water is a polar molecule. So we have a polar molecule that is attracted to the clay, and that makes it much more difficult for water to move through clay than compared to like sand, for instance, where the void sizes in between sand grains is really large. So you think about a pipe. Water is flowing through the pipe, so to speak, of the interconnected voids in sand. And if the void size is large, it's like water flows through a big pipe with very little resistance. But then if you consider the interconnected voids in clay, it's a really small diameter pipe that water can move through much more slowly. And so the hydraulic conductivity takes that effect into account. Not only the size of the void, but also the hydraulic conductivity is going to take into account the attraction that the liquid molecule has with the solid that's there. And sand also has a negative charge, but because the size of the particles, sand particles, are so much larger than clay particles, the charge isn't as intense. So when we later on start to look at some models that approximate how quickly water penetrates down into the subsurface, some of the things we have to address is what kind of a soil it is. And there is a soil texture triangle that kind of is a way of visualizing the relative ratio of sand, clay, and silt. And then what we call soil is determined by the percentage of each of those three constituents. And so in places where they're really fortunate to have large particle sizes and the water infiltrates really easily, like in the coastal plain areas of North Carolina, South Carolina, where there's a lot of sandy soils, the water can infiltrate really quickly. Here in West Virginia, I'm sure you already know, what we mostly have is clay soils. And so clay soils are just a real challenge, not just from a structural standpoint, but also water doesn't infiltrate as easily into clay soils. So some of the other terms that we have to be aware of when we're classifying the soil types and looking at the hydrologic implications is the porosity of the soil. So porosity is just the ratio of the pore space, or you can think of it as the pore volume, relative to the overall volume of a soil sample. And generally speaking, what's kind of ironic is that clay soils typically have a higher porosity than sandy soils do. And so if you were just considering porosity on its surface, you might think that water is able to travel through clay more easily than sands, because the more pore space there is, in theory, the easier it should be for water to go through it. But it's not just the porosity, of course, it's also the size of those pores rather than just the fraction of the pores that really counts. Field capacity is an important characteristic because what the field capacity describes is how much moisture is left in the soil after it drains by gravity. So after it's rained and the water has had a chance to drain out of a soil, how much water is still in there, without any temperature being added, if it's just gravity drained. And we can see that the clay soils hold on to a much greater proportion of water than the sandy soils do. They'll drain out to where the water is just wetting the outside surface of a sand grain, but the voids that are large, the water drains out of those large voids really easily, whereas the voids are smaller in clay soils, and so less of the water has drained out after precipitation. Now, if it's fully saturated, then the water content will be equal to the porosity. So during the storm, how this is saying the field capacity is after precipitation and after draining, so the water content can be a maximum at the porosity, and then through draining it will go down to the field capacity, but then the wilting point addresses how much the soil is holding on to the water and won't actually even give it up to plants where the root structure is going down through the soil. And so the wilting point of 20% for clay, what that means is that at 20% water content, the clay is going to hold on to any remaining water with so much force that the soil isn't able to extract, that a plant isn't able to extract it from the soil. Whereas clays, but on the other spectrum, the sands don't hold on to the moisture as tightly, and so you could get down to 5% water and still get plants able to extract the water from that fine soil. So the interpretation of all three of these trends, I think, is that the moisture moves more easily in sandy soils than it does through clay soils. So underground, in the unsaturated zone, meaning above the water table, where air is in some part of the voids, the voids are partly moisture, partly air in the unsaturated zone. Down there, we can think of how eager the soil is to accept additional moisture, and it actually creates a suction tension in the unsaturated zone that we can measure by pouring water into the soil. And you may remember the capillary effect, probably in your fluid mechanics course. The capillary effect maybe even was something that you did a lab on where if you dip a small diameter glass tube into water, then the water level rises. And the smaller the diameter of the glass tube, the higher the water level will rise, because the surface tension force is proportionally greater than the weight of the water that's acting downward in a small diameter tube. So we can do an experiment to see how eager the soil is to receive additional water. And it's a soil property that we can measure, this tension pressure, where if you have a tube that's full of water and you stab that tube down into the soil, then the soil sucks the water out of the tensionometer and it creates a vacuum in the headspace, and the intensity of that vacuum can be measured with a gauge, and we can graph, as a function of how saturated the soil already is, what the tension is for different types of soils. So a clay soil that is not saturated is going to have a really high tension pressure, but then as you start off with more water in the soil, then it's not going to suck the water out of this tube with quite as much force. And of course, a sandy soil would never have as much of a suction force, because it just doesn't have the same attractive potential between the water molecules and the soil grain as you've got with clay. So this is a physical experiment that we can do, and it helps to explain the movement of water through the unsaturated zone. Below the water table, we sometimes call the zone below the water table as the saturated zone, or the water table above it sometimes is called the vadose zone. That phrase is used a lot in like environmental engineering. It's also called the zone of aeration, but it's the water, the rain that comes from the sky and then hits the ground surface. How quickly it infiltrates down into the soil determines how much water would be then running over the surface. And so it's the movement in this unsaturated zone that describes how quickly the water moves towards like a stream. If there is a stream or a pond that's adjacent to the surface, then that inner flow can be an important part there. How easily the water can be absorbed by plants and evapotranspirated back into the atmosphere. This figure is it is a representation of the amount of water and the pressure head, and it's negative here because it's a suction. It's the similar kind of experiment we saw with the tensionometer, where if the water is fully saturating all of the voids, then there isn't going to be a suction tension pressure at all. A certain amount of pressure head will take you down to the field capacity, which is, remember, it's just draining by gravitation. The wilting point is where plants are no longer able to get water out of the soil. And so after a storm event and after it's totally drained, this range is how much water is available in the soil for plants to use. And then the hydroscopic water is just the tightly held thin liquid layer that's around the outside of the soil grain. And so we say that any amount of water between there and air dried or oven dried is just totally unavailable for use by plants. So this profile is saying the amount of water as you get further down into the soil from the surface. So here's the water table, and it's fully saturated. And so the pressure is going to be increasing as you go down into the groundwater, because that's the slope of that line is going to be the unit weight of the water. As you go down into the groundwater, the pressure is increasing, but it's a negative pressure as you go above that because of the soil tension effect. So here in the capillary fringe, there's a little bit more water than there is in the intermediate zone, because as you're closer to the water table, some of the water gets sucked up from the groundwater, and it's not fully saturating all of the voids, but some of the smaller diameter voids have a little bit more water than they would in the intermediate zone. And then here at the surface is where, when it rains, there can be a wave of water that floods down really quickly from the surface. And so the equations that predict how readily water will be accepted by the subsurface look at this profile of pressure and look at a profile of water content and try and mimic what happens during there being a ponding at the surface. Like when there's a sudden influx of water, then that water is going to be sucked down from above, but then over time there will be a declining potential rate of infiltration because the driving force decreases. So infiltration is simply just the amount of water that's penetrating into the soil and the rate of that water. And it can depend on whether you have vegetation at the surface, because having plant roots that penetrate down into the soil can help promote the movement of water down through the surface. Whereas if it's like a dusty surface with lots of fine grains, like a fine grain dust clogging up the pores, then water isn't able to infiltrate quite as easily. And so if the soil has been disturbed at the surface or compacted, then those are both effects that can reduce the amount of infiltration. So it's partly what's at the surface, but then it's also in large part what type of soil there is below the surface. So the porosity, hydraulic conductivity, and so on, the conditions of the soil underneath the surface. So the unsaturated flow is just movement of the water where there is some air in the voids. So below the water table, all of the voids are fully saturated with liquid, but above the water table, it's not that the soil is totally dry, it's just that the voids are partly air and partly moisture, some mix of the two. So the soil moisture will gradually increase as a wetting front moves down through the soil column during a rainfall until it becomes saturated. And that water table can rise when it's rainy, and it can fall when it's dry weather. And the movement of the water table also affects how quickly the water infiltrates down into the soil. This is showing beneath the surface, once it starts raining, where does the water go? And so this is showing the rate relative to the precipitation rate, like how quickly, for instance, how the infiltration rate changes over time. And this is really the most important of all of these rates. As engineers, we're mostly worried about how quickly is runoff coming from the surface. And so this curve is called the declining rate of potential infiltration. So at the beginning of a storm, when it just starts to rain, you have a high rate of infiltration, but then the rate of infiltration decreases because as the voids get filled with water, there's less of a driving force. The suction pressure decreases. When the soil isn't dry anymore, it's not going to be as eager to accept additional water. So this is a curve that we see repeated over and over again, regardless of what method we use to predict infiltration rate. The declining potential rate of infiltration is an important factor. Now the rest of these trends, we can also be aware of the fact that the amount of surface storage is also going to be declining as all of the ponds and the puddles get filled up during a rainfall event. Then the amount of available storage to accept additional water is also decreasing. This is some of the terms that I think are on that handout that I've shared with you before, the terminology handout. So the zone of saturation is below the water table where all of the voids are full. The zone of aeration means that it's partly air, partly moisture above the water table. So the atmospheric gases can circulate in the zone of aeration. And we can further divide the zone of aeration up into other categories. The capillary zone is what's closest to the water table, where there's just a little bit of extra water being sucked up into the fringe. The soil water zone is closest to the surface, and sometimes the moisture content is a little bit higher in the soil water zone, where the vegetation root is found and is able to kind of enhance the infiltration of water. So this is showing the cutaway, and each of those three zones. Capillary is closest to the water table, soil water zone is closest to the surface. And so this is water content. As you get down to the water table, the moisture content is saturated. As you get further away from the water table, the moisture content decreases until you get to some minimal moisture content. And this is before a storm starts. Think about once the water starts to hit the ground surface, then the moisture content is going to increase at the surface the most.
So the question is how can we describe the curvature of this and what happens to it during a storm? That surface tension effect is drawing the water up, but it'll also be drawing the water downward when water accumulates at the surface. And the way that we measure that tendency for water to penetrate quickly, remember, is the suction head psi. And that can be measured in terms of centimeters of water of suction. And one of the ways to measure that is with an infiltrometer. An infiltrometer can be as simple as just a ring of metal that you fill water into, and then you measure, like with a stopwatch and a ruler, how quickly the water decreases in height as it penetrates down into the soil. So this cross-sectional view kind of gives you an idea that when the water leaves the infiltrometer ring, it's penetrating downward, but it's also kind of going out sideways a little bit. And so that doesn't give us the best idea of what would happen during a rainfall event, because in a rainfall event, water would be spread evenly over the entire surface. So water wouldn't be going out sideways when it's raining. Water would only be going downward as it rains. So this single ring infiltrometer is not the best for estimating how the soil would actually absorb water. And so to kind of account for that, the double ring infiltrometer says if we have this outer ring of water that's being used to satisfy the sideward movement of water, then the stuff that's in the inner ring is just going to be satisfying the downward movement. So you can measure how quickly the inner ring drops, and from that determine, in the soil, how deeply it penetrated, and this outer ring is just kind of like causing the sideways movement. And so it's a way of isolating the downward effects from the sideways effects, and kind of like a field method for estimating infiltration rate. Of course, you have to be careful when using this not to scuff up the soil surface. You'd want to, when you're preparing the surface, have it be representative of the conditions everywhere else in the watershed as they actually are. So you'd try and put this into place maybe in several different spots and come up with a weighted average of the infiltration rate to get an idea of really what's going on everywhere in the watershed. If we take a unit volume in the subsurface, then the porosity is the ratio of voids within that total volume. And one of the earlier figures we looked at said that depending on the soil type, porosity kind of varies from about 25% to around 40%. Maybe in clay soils even higher than that, potentially. Soil moisture content is the ratio of water volume to total volume. Now, soil moisture can never go higher than porosity because, if all of the voids are full, then the water can't soak into the soil grains themselves. And so the maximum soil moisture content will be porosity. So the soil moisture varies from 0 up to the porosity. And when you have saturation, then soil moisture content equals porosity. What we'll be quantifying in a couple of the equations we look at is the change in water content during an event. So during a storm, when the water is penetrating down into the soil, it'll go from the initial water content to fully saturated. And so that change from the initial to the saturated moisture content will be delta theta. And then after the soil drains, then it has a residual moisture content of theta sub r. I think that probably effective saturation is something that you have seen before in soil mechanics class, and that is at a certain given point, like with the conditions as they are now, so this water content theta minus the residual water content, so that's in the numerator, and that equates to how much available moisture there is at a given time. So the difference between how much moisture there is now and how much there will be after it drains. So that theta sub r is the residual moisture that really can't be used by plants, can't be extracted by draining. So the available moisture content divided by the effective porosity. So the effective porosity is saying, you know, the voids minus the residual content, it's the amount of water that could be there if it was fully saturated, minusing out the water that has nowhere to go because it's so tightly bound to the water. Of course, Darcy's law is one way of measuring soil characteristics and how easily water moves through a column of soil. And this is the figure that's in your book related to Darcy's law. Figures like this, I mean, because I've seen it so many times, it makes sense to me, but for whatever reason, having the column of water sideways makes it a lot easier for me to understand, at least. If we have a reservoir of water and the water is flowing from an upper reservoir to a lower reservoir, then we have some surface area. We'd call that A. And of course, the water is flowing at a certain flow rate Q. And the difference in elevations, so here's the delta H between the two water surfaces. Now, of course, it's the same thing here. It's just the column is vertical instead of horizontally oriented like I've drawn on the board. But then they're also showing that this needs to be a constant head. So on the right side, this little reservoir of water that's connected, they have an overflow and an inflow so that the water level never changes as the water's flowing through the sand. You have a constant head at the inlet and a constant head of water at the outlet, so that you always have the same H values, so it can come into equilibrium, and then you're measuring the flow rate through the soil as it does that. And Darcy's law says that there's some proportionality constant that describes the ratio of the area, the slope of the energy grade line through the soil. So that is the difference in heights over the length of the soil column that it's passing through. And that this proportionality factor K will tell you what the flow rate through that soil is going to be. And so if K is bigger, that means that you'll have a higher flow rate for a certain driving force. And it's this delta H divided by the length of the soil column that it's flowing through, that's the driving force. It's kind of what's pushing the water through the soil is the difference in elevations. And so here, where we have the higher elevation on the left, the lower elevation on the right, if you have a bigger deflection in H, that'll be a larger driving force and the flow rate will increase. So that's one way to have a big Q, is by having a big delta H. Another way to increase the flow rate would be to have a larger cross-sectional area. But really what speaks to what's going on in the soil is captured by K. And that's going to reflect like the size of the voids. It's going to reflect the charge of the particles. It's going to reflect those properties that are kind of inherent to the type of soil that it is. So hydraulic conductivity has units of length per time, and it's a really important parameter for predicting flow rate. Now, sometimes Darcy's law is expressed differently, like they'll call J The driving force, J, would be the difference in elevations divided by the length. And sometimes Darcy's law is expressed in flow per unit area. So lowercase q would turn that into a flux if you are finding out how much flow there is for every unit of cross-sectional area that the water can pass through. So Darcy's flux has this formula. But I usually use the full hydraulic conductivity equation there. Just to refresh our familiarity with Darcy's law, let's finish by doing this example problem. If we have a fine sand, if you look that up in a table of typical hydraulic conductivities, it might tell you have hydraulic conductivity of 3 meters per day. So let's find out what's the flow rate in terms of liters per day. What's the flow rate through a column of soil that's 1 meter long, 25 centimeter diameter, and then where the head differential, delta H, is 35 millimeters. Well, eventually, let's get liters per day. It's going to give us, when you plug in the given values in terms of cubic meters per day, but it's pretty small. So if we multiply that by 1,000, we'll go from cubic meters per day into liters per day. I think we should see it's about 5.15 liters per day. The other time this semester that Darcy's law and K values is going to be really important is when we start talking about well performance. At the end of the semester, we'll spend almost our entire semester dealing with surface hydrology. But towards the end, we'll look at laws that describe when you're trying to pump water out of an aquifer, how much the drawdown in the water table affects the rate of movement towards the aquifer. And so those equations are pretty interesting, and we'll see K values again. So here's where we're heading next time. When we get together on Tuesday next week, we're going to look at methods for predicting how quickly water penetrates down through the soil. So experimentally, you can measure it directly, but you don't always have access to a site. You may have some basic information about the types of soil in a watershed, but maybe you can't actually go out and measure the infiltration. So there's a variety of different methods that empirically try and answer the question, how quickly is water infiltrating, and over time, how does that infiltration rate decrease as the soil voids become progressively more saturated with water. Here, a wetting front moving down through the soil. So at a given time, it's fully saturated at the surface, but if you go deeper down, there's just a small increase in water content. And so consider this curve. What it's saying is, as you go closer to the surface, as you go up towards the ground surface, the moisture content is increasing until it gets to saturated. So this curvature is showing an increase in the wetting front. Now here's the water table. So of course, below the water table, it's fully saturated. So the moisture content is equal to the porosity at that point. But as you get away from that, the capillary effect means the moisture content decreases a bit. But then during a rainfall event, when there's ponding at the surface, the water penetrates not all at once. It doesn't go from like normal water content to fully saturated. There's this curvature here, like a gradual increase. And that's what we're seeing in this video, is we're saying that it may be saturated at this point, but this isn't fully saturated. If it was, it would be penetrating through the sand, because we see what happens when the voids are fully saturated. The sand immediately becomes like a highway for that water to pass through because it has such a high hydraulic conductivity. So that hydraulic conductivity effect doesn't kick in until saturated conditions. So I just wanted to pause. We'll continue finishing the video there. But that's an important point, and I also wanted to tie it together with these figures that we're going to look at. And these figures seem abstract when you just see them for the first time and you're not able to kind of relate it to this visual representation of the water penetrating down through the soil. So what we're seeing is the wetting front go downward and outward because of gravity and because of the suction/tension within the soil. So those are the two things that are bringing the water down. But then the difference between full saturation and just an increase in moisture. All right, so in the video she talked about the movement of water when it's under pressure and the movement of water when it's under tension. And water is under pressure when it's fully saturated. So consider the water table. I think we had a figure on a previous lecture. Let's see if I can find that one. Yeah, here. All right, so here's the pressure profile where we're down below the surface, and then here's the water table. So if you go below the water table, then the water exists under pressure, and it'll move one way. But when you're above the water table, in the capillary fringe, there's water that exists under conditions of tension, meaning that the attraction for the soil is sucking the water grains away from one another, and so that it's making space between the soil grains for those voids to have air in it in addition to water. And so the movement of water is different if you're below the water table, meaning saturated, or above the water table, meaning unsaturated. But we don't only have unsaturated flow in that capillary fringe. The unsaturated flow also occurs during a wet weather event as the water penetrates downward through the soil. So just as a refresher, remember that we have under the soil voids that are containing some water and some air. And this illustration is showing that we have solid particles that are covered by a thin layer of water, and then in the space between those thin layers of water, the air exists. And the smaller the grain, the more tightly bound the water will be to the solid particle, and the higher the suction or the tension will be when we have unsaturated conditions. Okay, so here's this figure that I already kind of showed you, that under ordinary conditions, the moisture content decreases as you move upward from the water table until you come to some like initial moisture content prior to a storm event. But then as water ponds at the ground surface, then the wetting front moves downward through the soil. And the speed of its movement depends on the gradient between the initial moisture condition and what it will be at saturation. It depends on the hydraulic conductivity of the soil, and it depends on how deeply ponded the water is at the surface. So there are a lot of things that affect how quickly the water is going to penetrate down. And so what we need is some sort of an equation that accounts for those factors, like an empirical equation that allows us to predict how quickly the water goes down. And why? Why do we care about all this? Remember, the rainfall that hits the soil has two places to go, broadly speaking. It can either go into the soil or it can go over the surface towards some point of concentration, towards a watershed outlet. So runoff equals rainfall minus infiltration is the broad way of looking at it. So during a rainfall event, as there's ponding at the surface, then the soil capacity to absorb water decreases. The rate of infiltration declines over time because there's going to be a smaller driving force. The initial driving force, what we saw is that at first in those videos, the water penetrated downward and sideways very quickly because there was a lot of suction. But then as more of the grains become filled, there's a smaller driving force that that suction or tension head decreases. Okay, so this is what happens during infiltration. At the surface, the voids are completely saturated because we assume that there's a little bit of ponding at the surface. The water is distributed into the soil grains completely, and so this curve of moisture content goes from fully saturated, and then there's this transition zone that's a lot like the capillary fringe. In the same way that, you know, there was kind of like the standard water concentration and then some connecting the curve between fully saturated and the middle ground where partially saturated. So this curved zone here, it's kind of like we've reversed that, and now this transition zone is the equivalent of the capillary fringe. And so some of the voids have small diameter, some of the voids have big diameters, and the split between the two affects the shape of that transition zone. This is a really complicated curve for us to be able to model directly. And so instead of modeling it directly, the green-amped method, which is the most sophisticated of the two methods I'm going to share with you, says that we're going to have to assume the wetting front moves as a solid wave, that this transition zone is kind of neglected. And so that is one of the limitations of green-amped, is that it assumes that you go from immediate transition of the initial moisture content to fully saturated. It's modeling saturated flow rather than unsaturated flow. But in spite of that, it does a pretty good job of describing the curve of declining rate of potential infiltration.
So let's just say what on the left side represents going from partially saturated to full saturated?
Yeah, so here is fully saturated. This vertical line means that as you go down through the soil, the moisture content stays the same. And then this is the zone that hasn't been affected by the rainfall yet. So there is a zone of saturation, but then the transition zone is where there's a little bit more water than there was originally before the storm, but there is also some air in the voids. And so this is the unsaturated flow, which is associated with the transition zone. Austin?
So this is assuming that the water table is below all this, right?
Yeah, the water table would be below this and not shown. That's right.
So the line itself, like the data it's representing, is that the flow or is it like the moisture content?
It's the moisture content. Yep. Yep. And so here in green-amped, it's saying unsaturated flow is too complicated. Let's throw up our arms, give up a little bit, neglect this curved region, and just try and predict how quickly the water's penetrating based on saturation. And so if we think about what's really going on, and it can be thought of in terms of the Darcy's law. Remember, Darcy's law is the hydraulic conductivity and then some cross-sectional area that the water is flowing through, and then the driving force, where H1 and H2 is some elevation gradient between the upstream and the downstream location, and then L is the length over which the flow occurs. Well, the green-amped simplification says let's use those same kind of ideas. Now, instead of doing it on a volumetric basis, let's just take the area parameter out. So if we took the area parameter out of Darcy's law, then it would have units of length per time instead of units of volume per time. So if it was just K times H1 minus H2 divided by L, it would say the speed that the water is moving through the column of soil. And that's what this green-amped simplification says, is it says let's measure the driving force. And the driving force is the depth of ponding at the surface, so that's H naught. That's, you can think of the water being pushed from above, and then the second term is how much the water is being pulled from below. So it's the suction. Psi is the symbol. We looked at a table of different types of soil and how much suction they have, where clay has a lot of suction, a loam would have slightly less, sand and gravelly soils have an even lower suction head. And so the more this length expands, that's going to result in a decrease of the total overall suction. When this L is very small, there's a lot of suction capacity because you've got a big depth of soil and all of it is eager to receive the water with a really high tension. So over time, as the wetting front penetrates deeper, the driving force decreases. As the length increases, then the driving force decreases, and so the infiltration rate slows down. So this lowercase f has units of centimeters per second. It's a rate or a speed, the speed that the water is moving down through the soil. If we integrate that over time, we want to know the cumulative infiltration that's occurred to a certain point, then that's uppercase F. And the way that that's modeled is just by looking at the rate of infiltration over time and integrating that from the start of the rainfall event up until T, the time in question. And this figure kind of shows both the declining rate of infiltration and then the increase in cumulative infiltration, but also it's beginning to plateau, and it'll eventually reach some maximum value that it doesn't go above. So look at the rainfall. You know, initially there was a pretty high rainfall intensity, then the rainfall decreased a little bit, but in each of these cases, the rate of rainfall was greater than the infiltration rate. So that means that there's going to be ponding at the surface. There's more water at the surface than can be absorbed by the soil. And the green-amp simplification requires that. It won't be accurate. It'll be even less accurate than usual if we don't have ponding at the surface. So that's one of the things that I have to tell you, is that the Hydrologic graph of rainfall needs to be above the infiltration curve for us to have any hope of accuracy. And essentially what we're seeing is a column of water penetrating down through the soil, and there's this immediate increase from the initial moisture condition to full saturation, where L is going to be, over time, the length that that water column penetrates down into the soil. So we could know what's the cumulative infiltration amount by looking at how much of the pores filled up. Like the volume of water that was absorbed is going to be the initial moisture content minus the overall porosity minus the initial moisture content. And so that's kind of like a fraction, remember, a storage fraction. So it went from fully saturated, when the water penetrates all the way down, so the porosity is totally full with water. So the physical length of this soil, like if the wetting front goes 10 centimeters, it's not that it was 10 centimeters of actual water that was infiltrated, because remember, some of this depth is occupied by solids, and there was some water there to begin with. So a 10 centimeter L does not mean that there was 10 centimeters of rainfall. You know, 1 centimeter of rainfall may cause L to be 3 centimeters, or even more if there was a pretty high moisture content to begin with. But I just wanted to point out the difference between the penetration depth is not the same thing as how much was actually infiltrated. Just because it's a matrix of, we go back to that figure, to begin with, there is solids and some initial water. So the volume between here that's filled with air initially, that's the only place that the incoming water can go. And so if we have 1 unit of water, it's going to infiltrate much deeper than 1 unit of depth.